You know, people ask me all the time, what is a field? And I have to tell you, this is one of those questions that sounds simple, but it gets right to the heart of what we mean when we say we understand something in physics. Most people think they know what a field is. They imagine these invisible lines floating in space, like those iron filings around a magnet you saw in school, and they think, oh, that is the field. But that is not quite right, and I want to explain why. Because when you really dig into what a field is, you find something much stranger and more beautiful than just lines in space. Let me start with the problem that made us invent fields in the first place. Suppose I have two charges, two electrons sitting in space some distance apart. Now everyone knows they repel each other. You move one, and the other one feels a force and starts to move too. Okay, fine. But here is the question that bothered people for centuries. How does one electron know the other one is there? I mean, really, think about it. There is empty space between them. How does the information get across? In the old days, Newton had the same problem with gravity. The sun pulls on the Earth across millions of miles of empty space. How? Newton himself said he found this idea of action at a distance absurd. He said, I am not going to make hypotheses about it. I am just going to describe what happens mathematically, and his equations worked beautifully. But the question remained, what is actually happening in that empty space? Now you might say, well, maybe the information travels instantly. You move the electron here, and instantly, faster than you can blink, the other electron over there knows about it and responds. But we know that cannot be right. Einstein showed us that nothing, no signal, no information, nothing can travel faster than light. So if I wiggle an electron here, there has got to be some delay before an electron way over there responds. The information has to travel through space, and it travels at the speed of light, not faster. So something is carrying that information. Something is in the space between the charges. That something is what we call the electromagnetic field. But now I have to be very careful because I do not want you to think of the field as just some kind of invisible jelly filling up space. It is not a substance. It is not made of anything. The field is a condition of space itself. It is a number, or really a set of numbers, at every point in space telling you what force a charge would feel if you put one there. Let me put it another way. Imagine you are mapping out a room. At every point in the room, you could write down the temperature. Over here it is 70 degrees. Over there it is 72 degrees. Near the heater it is 80 degrees. The temperature at each point is a number. And if you write down all those numbers everywhere, you have made a temperature field. Now the electromagnetic field is like that, except instead of temperature, what you are writing down at each point is the force that a charge would feel. And that force has a direction too, so really you need to write down a little arrow at each point, showing which way the force points and how strong it is. But here is the thing, and this is crucial. The field is not just a mathematical convenience. It is not just a way of keeping track of forces. The field is real. It has energy. It has momentum. You can make waves in it. When you wiggle a charge, you create a disturbance in the field, and that disturbance propagates outward at the speed of light. That disturbance is what we call light. Light is just a wave in the electromagnetic field, so the field is not some abstract thing we invented to make calculations easier. The field is actually there, doing things, carrying energy from place to place. Now let me tell you how Faraday thought about this, because Faraday, he was the one who really understood fields before anyone else. Faraday was not a mathematician. He could not write down fancy equations, but he had this incredible physical intuition. He imagined space filled with lines of force. If you put a charge somewhere, these lines would emanate from it, spreading out in all directions. Another charge somewhere else would feel these lines, and that is how it would know to move. Maxwell came along later and turned Faraday's intuitive picture into mathematics, and what beautiful mathematics it was. Maxwell wrote down just four equations, that describe everything about electricity and magnetism and light. Those equations tell you how charges create electric fields, how currents create magnetic fields, how changing magnetic fields create electric fields, and vice versa. And when Maxwell looked at his equations carefully, he found that they predicted something nobody expected. They predicted waves of electric and magnetic fields traveling through empty space at a particular speed, and when Maxwell calculated that speed, it turned out to be exactly the speed of light. That is when people realized, my God, light is an electromagnetic wave. It is a ripple in the electromagnetic field. But I still have not told you what the field really is, have I? I have told you what it does, how we use it, but not what it is. And here is where I have to be honest with you. I do not know what it is. Nobody does. We know how to calculate with it. We know how to predict what will happen. But if you ask me, what is it made of? What is the ultimate nature of the field? I cannot tell you. And here is the thing, maybe that is the wrong question. Maybe asking what the field is made of is like asking what energy is made of or what time is made of. These are not things made of other things. They are fundamental aspects of how nature works. Let me give you an example of how we use fields to understand things. Suppose you have a radio station. The station has an antenna, and it pumps electric current up and down that antenna very fast, millions of times per second. That oscillating current creates an oscillating electric field around the antenna. And that oscillating electric field creates an oscillating magnetic field, and that oscillating magnetic field creates more electric field, and so on. The fields keep creating each other, and this disturbance, this wave of electric and magnetic fields, spreads out from the antenna at the speed of light. That wave travels through the air, through walls, through space, until it reaches your radio antenna miles away. Your antenna has charges in it, electrons, and when the wave passes by, the electric field in the wave pushes those electrons back and forth, creating a current in your antenna. That current gets amplified and sent to a speaker, and you hear music. The energy traveled from the radio station to your radio through the electromagnetic field. Nothing else carried it. The field did it. Now here is something even stranger. In quantum mechanics, we learn that everything comes in little chunks, little packets. Light comes in photons. And you might think, okay, so the electromagnetic field is made of photons, but that is not quite right either. The field is the primary thing. The photons are, well, they are excitations of the field. They are little packets of energy traveling in the field. You can think of it like this. Imagine a stretched rubber sheet. That is your field. If you poke it, you make a wave that travels across the sheet. That wave is like a photon. The wave is not separate from the sheet. It is a disturbance in the sheet. The photon is not separate from the field. It is a disturbance in the field. And here's where quantum field theory comes in, and this is really the modern understanding of what a field is. In quantum field theory, every particle, not just photons, but electrons, quarks, everything, every particle is an excitation of a field. The electron is an excitation of the electron field. The quark is an excitation of the quark field. All of space is filled with these fields. All the time, even when there are no particles around. And when we create a particle, what we are really doing is exciting one of these fields, poking it so it makes a little wave packet, and that wave packet is what we call a particle. So when you ask what is a field, the answer is the field is the fundamental thing. Particles are not little billiard balls with fields around them. Particles are manifestations of fields. The universe is made of fields. That is it. Everything else, matter, light, forces, all of it comes from fields. Now let me tell you about the experiments that convinced us this picture is right. One of the key experiments is the Casimir effect. If you take two metal plates and put them very close together in a vacuum, they attract each other. Why? Well, the vacuum is not really empty. It is filled with electromagnetic fields, and in quantum mechanics, those fields are always fluctuating, even when there is no light around. Between the plates, only certain wavelengths of these fluctuations can fit. Outside the plates, all wavelengths can exist, so there are more fluctuations outside than inside, and that creates a pressure that pushes the plates together. This is a real effect. People have measured it, and it shows that the field is there, even in empty space, even when there are no charges around. Another experiment that shows the reality of fields is the Aharonov-Bohm effect. You take an electron and make it go around a little solenoid, a coil of wire with current in it. The solenoid creates a magnetic field inside it, but outside, where the electron travels, the magnetic field is zero. You would think the electron should not care about the solenoid, right? But it does. The electron's wave function picks up a phase shift, and you can measure this shift in an interference pattern. How does the electron know the solenoid is there if the magnetic field is zero where the electron is? The answer is the vector potential, which is another way of describing the electromagnetic field, is not zero outside the solenoid. The electron interacts with the vector potential, not just the magnetic field. This shows that the field, or the potential, is the fundamental thing, not just the forces. Let me go back to the basics for a moment and make sure we understand what an electric field actually is. Suppose I have a charge sitting still in space. That charge creates an electric field around it. At any point in space, the electric field is a vector, an arrow, pointing in the direction a positive test charge would be pushed if you put it at that point. The strength of the field tells you how hard the charge would be pushed. If I have a positive charge, the field points away from it. If I have a negative charge, the field points toward it. Now, if I have many charges, the total electric field is just the sum of all the fields from each charge. Fields add up. This is called the superposition principle. Magnetic fields are a bit trickier. Magnetic fields are created by moving charges, by currents. If you have a wire with current flowing through it, there's a magnetic field circling around the wire. If you take a compass and put it near the wire, the needle will point along the direction of the magnetic field. Now, here is something interesting. A magnetic field does not push a charge in the direction of the field like an electric field does. Instead, it pushes the charge perpendicular to both the field and the direction the charge is moving. This is why charged particles move in circles in a magnetic field. The force is always perpendicular to the motion, so it just bends the path into a circle. Maxwell's equations tie all this together. The first equation, Gauss's law, says that electric charges create electric fields. The more charge you have, the more field lines come out of it. The second equation says there are no magnetic charges, no magnetic monopoles. Magnetic field lines always form closed loops. They do not start or end anywhere. The third equation, Faraday's law, says that a changing magnetic field creates an electric field. This is how electric generators work. You spin a magnet near a coil of wire, and the changing magnetic field creates an electric field in the wire, which pushes charges around, creating a current. The fourth equation, Ampere's law with Maxwell's correction, says that currents create magnetic fields, and also a changing electric field creates a magnetic field. This last part, the changing electric field creating a magnetic field, that was Maxwell's addition, and it is what makes electromagnetic waves possible. When you put all four equations together and solve them, you find that they predict waves where the electric field and magnetic field oscillate together, perpendicular to each other and perpendicular to the direction the wave is traveling. And these waves travel at a speed that you can calculate from the equations, and that speed is the speed of light. Maxwell realized this and concluded that light is an electromagnetic wave. This was one of the greatest insights in the history of physics. Now, I want to talk about energy in the field because this is one of the ways we know the field is real. When you have an electric field or a magnetic field, there is energy stored in that field. You can calculate how much energy per unit volume, and if you add up all the energy in all the space where the field exists, you get the total energy in the field. When you send a radio wave from a transmitter to a receiver, energy is traveling through space. Where is that energy while it is in transit? It is in the field. The electromagnetic field is carrying it. The field has energy, and that energy is real. You can measure it. It can do work. Here is another way to see that the field is real. When you accelerate a charge, you create electromagnetic radiation. The charge radiates energy away in the form of electromagnetic waves. Where does that energy go? It goes into the field. The energy spreads out from the charge at the speed of light, carried by the electromagnetic field. Eventually, that energy might be absorbed by another charge far away, and when it is absorbed, the energy goes back into the kinetic energy of the charge. But in between, while the energy is traveling, it is in the field. The field is the carrier of energy from one place to another. And momentum, too. The electromagnetic field carries momentum. If you shine light on an object, the light exerts a force on the object. That is called radiation pressure. Where does that force come from? It comes from the momentum carried by the electromagnetic field. When the light is absorbed, its momentum is transferred to the object. This is not just theoretical. We can measure radiation pressure. In fact, some people have proposed using radiation pressure to push spacecraft using the light from the sun or from lasers to accelerate a spacecraft with a big sail. The momentum in the electromagnetic field is real. Now let me tell you about something that really shows how deeply strange and wonderful fields are. In quantum field theory, the vacuum, empty space with no particles, is not really empty. The fields are still there, and they are fluctuating. Even when there are no photons around, the electromagnetic field has quantum fluctuations. These fluctuations are called vacuum fluctuations, and they have real effects. They cause shifts in the energy levels of atoms. This is called the Lamb shift, and it has been measured very precisely. The vacuum fluctuations also cause particles and antiparticles to pop into existence briefly and then annihilate. These are called virtual particles, and although they do not last long enough to be detected directly, they affect things we can measure, like the magnetic moment of the electron. So the vacuum is not empty. It is a seething froth of quantum fluctuations in all the fields. This is the modern view. Space is not a passive stage where particles play out their drama. Space itself, or rather the fields that fill space, is active, dynamic, full of energy and activity even when we think of it as empty. Let me give you one more example of the reality of fields. When two electrons repel each other, how does the force get transmitted? In the old days, we would say, well, one electron creates a field, and the other electron feels that field and responds. But in quantum field theory, we understand this more deeply. One electron emits a virtual photon, a little packet of energy in the electromagnetic field, and the other electron absorbs it. The exchange of this virtual photon is what transmits the force. The force is mediated by the field, by the exchange of quanta of the field. Every force in nature works this way. Gravity is mediated by gravitons, excitations of the gravitational field. The strong force is mediated by gluons, excitations of the gluon field. The weak force is mediated by W and Z bosons. All the forces are interactions of fields. So when you ask, what is a field really? The answer is, the field is the most fundamental thing we know. It is more fundamental than particles. Particles are just excitations of fields. The universe is a collection of fields. And everything that happens, every force, every interaction, every particle, all of it is just the dynamics of these fields. Now, I know this is all very abstract, and it might seem like I am just replacing one mystery with another. You ask, what is a field? And I say, well, it is a condition of space. It is a number at every point. It is the thing that mediates forces. But what is it really made of? And I have to tell you, I do not know. I do not think anyone knows. Maybe that is the wrong question. Maybe the field is not made of anything more fundamental. Maybe it is just a basic feature of the universe, like space and time. But here is the beautiful thing. Even though we do not know what the field ultimately is, we know how it behaves. We can write down equations that describe it exactly. We can make predictions with those equations, and those predictions match experiments to incredible precision. Quantum electrodynamics, the quantum field theory of the electromagnetic field, is the most precisely tested theory in all of science. We can calculate things like the magnetic moment of the electron, and when we measure it, theory and experiment agree to 10 decimal places. 10 decimal places. That is like measuring the distance from New York to Los Angeles to within the thickness of a hair. So even though we do not know what the field is in some ultimate philosophical sense, we know how it works, and that is what matters in physics. I think what is important to take away from all this is that our intuitive picture of the world, little solid objects sitting in empty space, pushing on each other, that picture is not right. The world is much stranger. It is fields, everywhere, always, oscillating, interacting, exchanging energy and momentum. And what we call particles, the electrons, the photons, the quarks, they are just ripples in these fields. The field is the fundamental thing. The universe is made of fields. That is the deep insight of modern physics, and it is one of the most beautiful ideas we have ever come up with.